In this video, we're going to be looking at how to solve exponential functions. I want you to notice that I have some different strategies written that I'm going to show you in some of the different examples. And some of these strategies can be used on different problems, but I'm just showing you some examples of the different strategies. Also, we will be adding some helpful log relationships that come in handy when you're solving exponential functions as we go. But I do want to start out with one called the power property, because in our very first example we're going to use the power property. So if you recall, when we were talking about the history of logs, I gave you an example where I had log base 2 of 4 to the third, and I said you could rewrite this as 3 times log base 2 of 4. In other words, I can take the exponent and move it in front of the log. So if 4 to the third is inside the log, that is the same as 3 times log base 2 of 4 in this case. This is going to come in handy. So let's just kind of summarize it. If I have log base b of a to the c power, that is the same as c times log base b of a. So this is known as the power property. This can come out front. This is going to be helpful in our first example. So if we go to the first example, it says 3 to the x plus 4 equals 7. Now, there's no way I can just guess the number 3 to what power equals 7. I know it's going to be somewhere in between 1 and 2, that this number, that x plus 4 has to be somewhere in between 1 and 2, because 3 to the first is 3 and 3 to the second is 9 and 7 is in between those two numbers. So I know my answer is going to be between 1 and 2. And other than guess and check, though, I have no way to find that number specifically. So notice when we solve equations from Algebra 1, you've always learned that you do the same thing to both sides of the equation. So one thing I can do is take the log of both sides of the equation. And I'm just going to go ahead and use log base 10 because that is a commonly used log. So I'm just going to write log of 3 to the x plus 4. Remember, if I do not put a base, that is log base 10. Log of 7. Now here's where the power property comes in handy. The thing I'm trying to solve for, x plus 4 here, is in the exponent position. Because of the power property, I can take this expression and move it to the front. And I can do x plus 4 times log of 3 equals log of 7. Now it's very important that you use parentheses around the whole thing, because that whole thing is being multiplied by log 3. Now log 3 and log 7 are just log base 10 of 3 and log base 10 of 7. Those are numbers that I can just calculate. Those are numbers. They are not variables. So for my second step, I am just going to divide the whole side of the equation by log of 3. So now I have x plus 4 is equal to log of 7 divided by log of 3. So to solve for x now, x is log of 7 divided by log of 3, the whole quantity minus 4. And if I do that on the calculator, so let me open up my calculator. So log, now notice there's a place to put an extra base. If I just ignore that, it's going to automatically be base 10. So I'm just going to leave that off. Divided by control 10 to the x gives me log of 3, and then was it minus 4 or plus 4? Minus 4. Okay, minus 4. I'm going to do a control enter, so it will give me the decimal form. And I think I need to reset my calculator to have more decimal places. Just a moment. Actually, I thought it would be good for you to see how I do this. So if I click my battery icon and go to document settings, change float to 6 or so. You can have it be more if you want, float 8, float 6. That will give me more decimal places. So if I go up and do this again, okay, shows me more decimal places. I had it set for something during J-term, I think. Notice how this automatically evaluates this as log base 10. So negative 2.2876. Now, I'm going to go ahead and put the answer, but also let's go ahead and show how you would check the answer. Negative 2.22876. Of course, that is a continued number. So x plus 4, notice that if I add negative 2.22 whatever plus 4, that's a number somewhere in between 1 and 2, which is what I already knew, that it had to be a number, that this exponent had to be between 1 and 2. So if I were to check this, then I would just put 3 to the, and then go up and grab this number, plus 4, and that should give me 7. Perfect. Okay. Now, we are going to look at the same problem, but do it in a different way. And how you do it is totally up to you. So this is just another version. Remember, we talked about that we could rewrite an exponential form in log form. With the base is 3, the exponent is x plus 4, and it equals 7. So I can write this as log base 3 of 7 equals x plus 4. So log base 3 of 7 minus 4 equals x. Now this 7 is inside the log and the minus 4 is not inside the log, so you cannot combine that and make that number 3. Okay, so this is inside the log, this is outside the log. So if I do this on my calculator, control 10 to the x, so now I'm going to put in log base 3 of 7 minus 4. Okay, same answer. Now, that means that this expression, log base 10 of 7 over log base 10 of 3, is equivalent to log base 3 of 7. This is known as the change of base relationship. And we're going to put this in our helpful log relationships. Log base b of a is equal to log, I'll call log base c of a over log base c of b. So notice this number goes in the denominator, this number ends up in the numerator, but I use a different log base. Now what's the point of that? Well, a lot of calculators only give you log base 10 or natural log a over natural log b. So in order to calculate something like log base 3 of 7, I would have to make a change of base and write it like this. Log of 7 divided by log of 3 minus 4 equals x. Notice that's exactly what I ended up with over on the other side. Those are the same thing. Now, when your calculator is in press to test for a test, this base 3 and other bases besides 10 and log and natural log will not be available to you, so you will have to use change of base. So you're going to have to use this in press to test. So get used to thinking when you have log base 3 of 7 that you're going to have to write it as log of 7 divided by log of 3. Okay, another strategy is to use a helpful choice of log base. So when we are in base E, you're going to want to use natural log. Let's go back up here and think about this. Remember that log base b of b is equal to 1. Remember, because b to the first equals b. That gives us a very helpful relationship with natural log, because when we see natural log, this right here, that's the same as log base e. So we're saying log base e of e, which is just equal to 1. So natural log of e equals 1. So that's what we're going to want to use when we have a base e, because it's going to simplify very easily. And then just remember that log base b of 1 is 0 as long as b is not equal to 1 and b is greater than 0. So b can't be negative, b can't be 1 in a log base. And actually, I don't know how helpful that is for solving exponential equations, but I have it written down, so I'll go ahead and fill it in. Okay, so use a helpful choice of log base. So with e, you're going to use natural log. Always start by isolating the base with its exponent. So in here, the base is e. The base is not 4e, it's just e. If it were 4e, 4e would have to be in parentheses. So if the base is e, the first thing I'm going to do is divide by 4 to isolate the base with its exponent. e to the negative 1.2t equals 5/4. Then the second thing I'm going to do is take the log of both sides, but I'm going to use the natural log. Natural log of e to the negative 1.2t is equal to natural log of 5/4. And then I can use the power property to bring out the exponent. So it's negative 1.2t times natural log of e equals natural log of 5/4. Well, natural log of e is just equal to 1, because that's log base e of e. So I don't need that anymore. So it's negative 1.2t is equal to natural log of 5/4. So now I can say t is equal to natural log of 5/4 divided by negative 1.2. So let's calculate on the calculator what that equals. So natural log, you do control e to the x, where you have that little natural log above that. 5 divided by 4, and then divide that by negative 1.2. Control enter, and there's my answer, negative 0.1859, etc. And I'll write that on in just a minute. But let's go ahead and check our answer while we're at it. So it's going to be 4, and then we can say e to the x. Oops, that's not what I meant to do. 4, and I just hit this button, e to the x. That automatically opens the exponent position. Grab that. That's our, times negative 1.2. Forgot that part. So negative 1.2 times this, and that should equal 7. I'm sorry. Did I? Yeah, no, 5. I was looking at the wrong problem. It should equal 5, so that is correct. So let's go ahead and put the decimal form of the answer here. T is equal to negative 0.1859, etc. Okay, now, some of you may have said, do we have to take the log of both sides? Couldn't I just rewrite this in exponential form? Couldn't I take this right here? So I'm going to write or here. Could I just write that as log base e of 5/4 equals negative 1/2 t? Like basically like this, log base e of 5/4 equals negative 1.2 t. Or natural log of 5/4 equals negative 1.2 t, and then divide by negative 1.2? Yes, you could have gone straight to that step, and that's another way to do it. Okay, our last example in this video is a helpful choice of base. In this case, I noticed that 3 and 27 are both powers of 3, so I'm going to use log base 3. Because that's going to simplify things. So if I take log base 3 of 3 to the x equals log base 3 of 27 to the x plus 1, and then I use the power property to bring the exponent out front, I have x times log base 3 of 3 equals x plus 1 times log base 3 of 27. So log base 3 of 3, if we think about log base 3 of 3 equals what? We're saying 3 to what power gives me 3? That's just 1. Remember that in our helpful properties up here, log base b of b just equals 1. So this is just x times 1. And then this is x plus 1. Log base 3 of 27, 3 to what power gives me 27? That's 3 to the third is 27, so this is just 3. So by using log base 3, I simplified my logs really easily. So I end up with x equals 3x plus 3, or 0 equals 2x plus 3, negative 3 equals 2x. So negative 3/2 equals x. So if we check this, 3 to the negative 3/2 and 27 to the negative 3/2 plus 1, those should equal each other. I'm not going to go through the check on the calculator because they are correct. Now, there's also another way to do this. So I'm going to say, or, if you look at this, 3 to the x and 27 to the x plus 1, this only works if you have a common base. Okay, so this is 3, and this could be written as 3 to the third. So I can write this as 3 to the x equals 3 to the third to the x plus 1. Now I can use my exponent rules and know that if I raise a power to a power, I multiply the exponents. So I have 3 to the x equals 3 to the 3x plus 3. Now I notice that these are the same base, and so if they're the same base and the two expressions are equal to each other, the exponents must be equal. So x has to equal 3x plus 3, and then I can finish solving. So then I'm right where I was before, and I can finish solving. So those are two different strategies that if you notice that the base is a power, the power of the same number. Now I could actually have used this strategy with a helpful choice of base with any problem. So for example, I could have done this over here. I could have said log base 3 of 3 to the x plus 4 is equal to log base 3 of 7, brought this out front and said x plus 4 times log base 3 of 3 equals log base 3 of 7, and since log base 3 of 3 is equal to 1, I would have ended up with x plus 4 is equal to log base 3 of 7, which is exactly what I have here. Now that took an extra step, so I don't know if it's the best way to do it, but that's another strategy. Okay, so there are multiple strategies to use if you know your log rules and you know if you know what a logarithm means and how it works, then there are multiple ways to do some of these problems.